Hi everybody, happy Friday. If you remember, this week was your chance to kind of review how you did on the midterm. I posted a video on Monday explaining the answers to the midterm and kind of get clarification on topics that you were still uncomfortable with to make sure that we were all kind of on the same page before we move forward with new material next week. And we got one question this week about asking for clarification on multiple regression, and more specifically, omitted variable bias and the omitted variable bias formula. So what I thought I'd do is we could work through an example together to kind of show what each of those terms in that formula means and why we worry about omitted variable bias in the first place. So this is an article from The Atlantic called "The Financial Perks of Being Tall." And what they're pointing out here is that there is robust statistical evidence that people who are tall, especially men who are taller, earn more than men who are shorter. And I actually have this data set here. And you see when you regress income on height, you find that the coefficient is 7.92, so about $800. So what this is telling us, let me grab this. What this is telling us is that an additional inch of height is associated with an additional $800 in income. Okay? And the question that we want to ask as econometricians, as social scientists, is this a causal effect? Okay, and how do we know something's a causal effect? Well, remember we had that motto, there's no causation without manipulation. All right, so you might know that there's this awful surgery they can do to you where they basically break your legs and the bones kind of fuse together, and that can make you taller. So when we're asking, is this a causal effect, we're basically asking, could the government give that surgery to poor people and raise their incomes, right? Or, should you get that bone femur lengthening surgery to raise your income, right? If there's a causal effect, then you should. And if there's no causal effect, then all you're doing is making yourself miserable, or maybe you want to be taller. Okay, so we're wondering whether or not this is a causal effect. And one thing, but we do know that there is a correlation between income and height, right, in this regression. We call this the short regression. And this term right here, we're going to call it beta squiggly 1. Okay, so that's the relationship between income and height, not taking into account any other factors. And we're wondering if that's a causal effect. All right. One reason why it might not be a causal effect is if you have, so if you remember directed acyclic graphs, so there's some effect of height on income. Maybe it's very small, maybe it's even 0. But it's possible that there's some third variable that causally affects height and causally affects income. And if that's the case, if there is this underlying third variable, then this term here is not going to be an accurate representation of the real relationship between height and income, because this is measuring, this coefficient here is kind of like observing this path and this path at the same time. All right. So what we want to ask ourselves is there any variable, is there any factor that affects someone's height and affects their income. And what the article says, if you want to read the article, I'll link to it, and they also link to this ECON paper. They say that, they're saying that yes, there is an omitted variable. They're saying that basically kids who are more well-fed during childhood are grow up to be taller, and better childhood nutrition also improves your cognitive skills and makes you smarter, which would lead to higher income. Okay, so a way we could proxy for childhood nutrition, if we couldn't measure it, could basically just be your parents' standard of living. Okay, if you have really rich parents, then you're really well fed as a child. You grow taller, and you make more, and you also develop more cognitively, which leads to higher income. Whereas if you grow up poor, you're not as well fed, you don't grow up as tall, your cognitive skills don't develop as much, and your income is lower. Okay, so that's the argument, is that the effect, height doesn't really raise your income by $800 per inch. That surgery wouldn't actually help you, because the relationship between height and income is just kind of a mask. It's being masked by the effects of parents' standard of living on income, right? It's just kind of a proxy for that relationship. All right, and so how could we tell whether or not this is true? Well, what we'd want to do, ideally we'd like to somehow, we can't even randomize height, so our best case scenario is not an option. But what we'd really like to do is to take two families with the exact same income, but their kids are different heights, and then compare their kids. Okay. The issue is that that's not a lot of variation for us to exploit. Okay, because income is a continuous variable. We're not going to have a bunch of families with the exact same income in dollars to compare. So what we do instead, and what we talked about in the previous week's video on multiple regression, is we instead use multiple regression. We kind of, instead of trying to fit a line in 2 dimensions, we try to fit this kind of plane in 3 dimensions, and that enables us to kind of do the same thing. If you read the Angris textbook, it's talking about how regression is this automated matchmaker. It's trying to find the closest match in terms of income, and then comparing the income of, the closest match in terms of parents' income, that's an independent variable, and then comparing the income of children with different heights after the regression matches those families with similar incomes. Okay, so in our data set here, we have a variable for parents' income. Okay, so what we want to do to maybe control for the fact that people of different heights also come from families with different incomes, we want to regress income on height and parents' income. Okay, and that gives us this result. And let's bring it in here and let's see how it's different. Okay, so this here, because we have 2 variables instead of 1, we call this the long regression. Okay, and notice that the effective height on income goes from about $800 all the way down to about $100, and the kicker, if you look at the p-value, it's not even statistically significant anymore, so we can't even rule out the possibility that height has no effect on income once we control for the fact that taller people tend to come from richer families. Okay, and so these 2 coefficients, this one, height, we call this beta 1, and this one, parents' income, the control variable, is beta 2. Okay, so we have our short regression and our long regression. All right, and the fact that the effect of height is so much larger when we fail to account for this fact that taller people come from richer families, that discrepancy is omitted variable bias. Okay, and what we'd like to do somehow is, can we express this, the coefficient in the short regression, in terms of these two? So or maybe even express this in terms of these two. Okay, so what we can show using math is that if we run one more regression, this time what we're going to do is we're going to ignore income, present income altogether, and we're just going to regress your parents' income, how rich are your parents, on height. Okay, and we get this result. Okay, so we're kind of looking here at the relationship between our independent variables. Zoom out a little. Okay, so this is kind of we don't necessarily have a name for this. You could call it like the side regression. All right, but this value here, we call this gamma hat 1. All right, that's just terminology. That's the name we give for the relationship between the variable of interest and the emitted variable in the side regression here. All right, and what we can show, and this is, you can watch the proof of this in the slides, is that beta 1, the effective height once we control for the fact that taller people come from richer households, is equal to beta squiggly 1, this is when we don't control for anything, plus beta 2, this is the effect of family income, family standard of living on your income when you grow up, times gamma hat 1, the effect of height on the emitted variable. Right? And we can actually, if we bust open a calculator, all right, so let's start by multiplying beta 2, which is 1.13, times gamma hat, which is 603.6, 682. Okay, and then we want to add this to beta 1. Oh, sorry. This was written backwards, I'm sorry. Should be beta hat 1, beta 1. Sorry about that. Okay, so now we take this, we add in beta 1, which we can see right here, is 109. We get 791. That's pretty much exactly, the decimal points might have skewed our results just a tiny bit, but look, 791 over here at 792. So our formula works out, okay? So that's the idea behind the emitted variable formula. Emitted variable bias formula is we can actually quantify the relationship between our coefficients when we don't control for something important and when we do control for something important. It depends on whether or not, it depends on the relationship between our emitted variable and our dependent variable, and our emitted variable and our independent variable, okay? But, why does this formula matter? I mean, we should obviously just control for this. And the reason this formula matters is that you're not always going to have just a variable equal to parents' income in your data set. All right. Sometimes you're going to have, sorry, I'm just erasing all this. Sorry. A lot of our troubles in econometrics come from unobservables. Variables that are important, but they're either not in our data set or we can't really measure them. Okay. And the OVB formula can tell us, the effect of emitted observables. So if we go back to that spanking example, right? We see that, we see three effects. We see that spanked children are more likely to commit crimes as adults. Okay, you can think of this as beta squiggly 1, okay? And that's basically all we can observe, okay? We think that there's an emitted variable, okay? We think that, kind of rotten kids grow up to be rotten adults. There's, some nature component that maybe some people are just, more antisocial, okay? This is beta 2. And then the other fact is that rotten kids get spanked more. Okay. This is gamma hat 1. Okay. And this is all conjecture because we can't actually measure how rotten a child is, right? You remember that scene in Willy Wonka in the Chocolate Factory where, the girl steps on the scale and it says she's a bad egg, right? We don't have that measurement in the real world, right? So, kid rottenness. Ooh, what is going on? Sorry, still getting used to this drawing tablet. Kid rottenness, is that a word? Is an unobservable. It's important, but we can't just plug it into our regression, all right? But we can kind of speculate on, okay, what does leaving this out mean for our correlation that we're observing, the beta squiggly? All right, well, this effect is positive, right? Rotten kids grow up to rotten adults. There's a positive relationship between kid rottenness and adult misbehavior. This is also a positive effect. Okay, and so if you remember our formula that beta squiggly equals beta 1, this is the true effect. We're wondering, like, if we, if I randomly decide to spank one of my kids and not spank the other one, how much more rotten is the spanked one going to turn out to be as an adult? Okay. All right. We know that, we don't know the values of these. We can't actually get numbers because our emitted variable is unobservable. But we can pretty clearly guess at the signs. So, that's positive and that's positive. Positive number times a positive number. This whole bias term is a positive number, which means that this effect, this statement here, is the true effect plus an upward bias. So this statement is an overestimate of the true effect. Or, the true effect of spanking is closer to 0. Now, we don't know how much closer, but, working through the logic of emitted variable bias can at least tell us the direction of the bias when we exclude emitted variables. Okay, this is basically just a more quantitative version of the selection bias formula, right? It's a really important skill for you to develop to be able to say, okay, we can't plug this variable into our regression because we don't have it. What does leaving it out do to our estimated effects? Okay, and we'll see in future weeks more examples of that logic. Okay. But I hope this helps, help you think more about the emitted variable bias formula. I'll post a link to the article because they also explain the underlying logic regarding parental income and nutrition and how that can skew the observed relationship between height and adult income. All right, so again, good job on the exam. I will talk to you guys on Monday. We'll get back into just doing new material. I'll look forward to it. Thanks.